Hi, good afternoon. This is going to be the fourth and final lecture on the series on unified view of various constructions in topology. In the last three lectures, we are looking at natural maps between two sets X and Y, and one of them is equipped with a topology. Then we looked for an optimal topology on the other set, which makes the function continuous. Okay, and a little more elaborate, okay, like product. Okay, I have a set and a natural functions to two spaces, topological spaces. Then I look for the optimal topology, etc. So as special cases, we arrived at subspace topology, product topology, and quotient topology. Now today's lecture is the culmination. What we are planning to do is how to work with the newly constructed spaces. See, there is a very important principle in modern mathematics. Whenever a new mathematical structure is constructed out of old mathematical structures, okay, then how to deal with the new object. Okay, this is governed or explained by universal mapping property. So I am going to formulate that and show how to use universal mapping property in all these three cases, and you will also find some of the things day in and day out you have been using, okay, is explained for the first time. It will be very an eye opener, because you search for any book, one of this universal mapping property which I am going to formulate and prove, you will never find it, but that's a fact you will be using all out through in mathematics. Okay, stay tuned, we'll get to that. Yeah, so let us formulate the very first thing. Let us look at this. Suppose f is a function from x to y, and let us assume y has a topology. Okay, therefore we look for the smallest topology tau on x, so that f from x tau to y tau y is continuous. A special case was where a is a subset of x tau and j is the inclusion map to x. We got a subspace topology, right? Now, so this is a new thing. What is a new object now? New object is x tau. Now how do I work with it? Notice that again, and all through my lectures on mathematics, I always explain, when you want to understand the mathematical structure, okay, the most important thing is to look for maps which preserve the structure to similar objects with the same structure. Like if I have a group, then I look how group homomorphism from that group G to another group H operates. Okay, this is something like when you want to understand a human being, you try to see how this human being interacts with other human beings. Then you get to know something about the human being. So something similar. Okay, so I want to understand, suppose you give me z tau z a topological space, therefore y tau y, they are all given, they already have topology, there are in some sense whole topological spaces. The new monster is x tau. Now what are the things I should ask for? I should ask for a function. Since I already used f, let me use a function g. Okay, either z tau z to x tau when this is continuous. When is this continuous? Continuous, or the other way around, g from x tau to z tau z continuous. Okay, this is what I mean by either maps into the new construction or maps from the new construction when they are going to be continuous. This is the natural question I should ask. What universal mapping property says is it will answer one of these. It will talk about the continuity of one of these maps, either G, the first G or the second G. Are you following? So universal mapping property okay, answers about the continuity of one of these maps. I could have called G1, G2 or G and H, but I just used. Now, how do you get that thing? This is the trade sector I'm going to give. Okay, let's look at. So I have something like F x tau to y tau y. I have F. Now what kind of maps are available? Just to have a look at. What kind of maps are available? So I have x tau to y tau y. This is my F. Therefore I can either look at this map F G from z tau z, okay, or I can look at the other map z tau z to, if you want, call it H. Okay, so that I don't want to get confused. No, I already did that. I'm sorry, I already did that. So what I should go for is something different. H from here, right? Now which do you see that which you can compose? Either this picture is given or this picture is given, right? And in which one of them you can have a natural composition. You can see I can naturally compose this one. Do you see that? This is nothing other than F composite G, right? Y come to G and followed by F, I have a natural map. Here there is no way I can compose because the arrows are going in different directions. You see that? See, these are the things which are not taught, okay, never taught. So please spend some time, learn them. Have you see that? So the universal mapping property for this construction, that is UMP, okay, what it says is the following. It says the map G from tau z to x tau is continuous if and only if this I will write, this is never written there, but I am writing the natural composition, namely F composite G from z tau z to y tau y is continuous. Please spend some time. What is the advantage of this property? This is the theorem. Okay, what is the advantage of this? See, I want to look at continuity of a thing, a function G, from a space Z to newly constructed space x tau. Okay, now the continuity, to prove its continuity, okay, I only have to look at the continuity of a map between two existing topology spaces. They are not new. Z tau z to y tau y. What is the map? The very natural composition. Notice that in particular this never answered. Okay, so this is not answered at all. This aspect is not answered. In the universal mapping property is never answered. It answers only one part. Yeah, do you follow that? Okay. Yeah. So the proof is utterly trivial. Why? Suppose G is continuous, okay, by construction F is continuous, and therefore F comma G is continuous. Okay, therefore one way is proved. If G is continuous, then F composite G is continuous. Is that clear? So we want to prove the other way around. Converse is what we want to prove. Converse is, if F composite G is continuous, then G is continuous. We want to prove that. Yeah. So let us look at. Therefore G is a map from Z tau Z to to y tau y. I want to prove this is y, sorry, x tau x. I want to prove G is continuous. So what does it mean? You start with an open set U in tau x. What is that I want to prove? Okay, so question is to prove G inverse of U is open in tau z, that is it lies in tau z, right? But what is given to me now, since U is open in tau x, what does it mean? Remember, tau x was defined to be the collection of all f inverse of V, where V is in tau y. Therefore, when I say U is in tau x, then U is of the form f inverse B. Therefore, U is of the form f inverse B. Okay, I hope you had reviewed what we did earlier, so that it will be easier, otherwise you will be struggling. Yeah. Therefore, G inverse U, I want to prove that G inverse U is open, but G inverse U is nothing other than G inverse of f inverse U. But this is nothing other than f composite G inverse of B, right? But what do I know? It is given f composite G is continuous and V is open, where? In tau y. Therefore, this is in tau z. Yeah. Therefore, I have proved G inverse U is open. That means G is continuous. Yeah. Pause, review, proceed. Now let's apply this to our subspace topology construction. So how did we construct there? So I have a topology space tau, I have a subset A of x, and I looked at the inclusion map J from A to x. Then I put the tau subspace topology tau. Tau is the subspace topology on A. Okay, how did it look like? It is U intersection A, where U is open in tau x. Do you understand? Right. Now let's try to understand what does universal mapping property says here. What it says is, suppose I have a map Z, tau Z, to A tau, then this is continuous. If and only if, okay, J tau Z to x tau x, the composite map, okay, that is, what is the composite map? J composite G is continuous. Is that clear? But a picture will make the point very clear to you. So what I have is, I have Z, okay, and what I have is x, and I have A here, and my map G is actually a map from to this. Yeah, G is a map from where to where? The set Z to the set A, right? I want to talk about the continuity of G. Now what does it say is, you can think of G actually as a map from Z to X. Think of G as a map from Z to X. Now Z is already a topology, namely Z tau Z, and X has a topology x tau x. Then what does it say? It says that, okay, the map G from Z to A is continuous if only if the map G from Z to X is continuous. So what I am saying, think of G as a map from Z to X, but it takes values only in A. Think about this kind of subtle nuances is never explained. People want very easygoing things, and so the students never improve. Okay, take time. It may be slightly uphill task, but try to understand. So what does it say? It says that, let me repeat. So I want to consider G as a map from Z tau Z to A tau. Okay, is continuous. Okay, what it says is think of G as a map from Z to X, taking values in A. Okay, and then therefore it's a map. The G becomes a map from X to Z to X. Therefore G is a map from Z to X. Now if this map is continuous, if this map Z to X is continuous, then so is Z to G to A. That's what it says. In fact, it's if and only if. Okay, pause, review, proceed. As a special case, you should know, suppose I have a map from R to R, okay, and the map is f of x equal to x squared, let us say. Therefore I can think of this f as a map from R to this set. Okay, I want to know whether this map x going to x squared is continuous. It says it's a continuous. Okay, this is same as asking continuity of the same map f, but consider as a map from R to R. Okay, please pause, review, proceed. This is a very simple example. So you will see this kind of logic you are using throughout your life if you are stay in mathematics, of course. Yeah, okay. There is another question I should ask about, but I don't want, when I deal with the subspace topology I will come to that. Okay, at present I don't want to spend time on that because I want to concentrate only on universal mapping property. Next, second construction. Let us look at that. Second construction is I have two topological spaces, x tau x, y tau y, and the product map, product set, and I put the smallest topology on this. So I have to let tau be the product topology. So now let Z tau Z be a topological space. Then what are the two things I can talk about? Again, a picture will make life clear. Let us do that. So I have x cross y, pi x to x, and pi y to y. Now there are two things I can ask for: Z tau Z to G or H Z tau Z. I want to talk about continuity of, so we are worried about continuity of G and continuity of H. What do you think universal mapping property should deal with? If I understood my earlier point, you can quickly come up with this. So which are the diagram? Let's look at two diagrams. As I said earlier, there are two diagrams now. This is one diagram and this is another diagram. So which of the diagram admits a very natural composition? I'm sure all of you know. Yeah, the top diagram. Oh, I should have used this color. I'm sorry, I did not change the color. Maybe I should do, yeah, right, very good. Okay, let me just, so which the pink color or whatever you call this allows natural composition, that is Z to x cross y and projected to pi via pi x to go x. Therefore I have a map from Z to x, or Z to x cross y and projected via pi y. Therefore I have a map from Z to x cross y to y. So this is the natural construction, natural composition allowed. Whereas if I have H, then there is no way. Oh, again, I'm sorry, I keep forgetting. I'm really sorry. Today somehow I am not in correct way. Okay, my thinking is slightly clouded. So this one, maybe again I change the color. This one. Okay, this one doesn't. I'm sorry, go back. So either map from Z to X cross Y or X cross Y to Z. So this map, okay, this does not, okay, does not admit natural composition. Whereas this, there exists two natural compositions. So what do you think the result should be? Just make a guess, do not think, I write a statement and then prove it. Okay, we should learn how to think and make a guess, conjecture. What is the natural thing? Therefore, I would like to say Z is continuous if and only if the composition maps, both the maps should be continuous. That is, Z is continuous if and only if pi x composite G is continuous and pi y composite G is continuous. That must be my universal mapping property. Do you understand that? Yeah, that will be my guess. Let us go ahead. Okay, let us formulate it and try to prove it. So universal mapping property for products. So I have a map G from Z tau Z to X cross Y tau. This is continuous if and only if the natural compositions what are the natural composition? Pi x composite G from Z tau Z to X tau X and pi y composite G Z tau Z to Y tau Y are continuous. Okay, proof is again easy. You will be very surprised to see the proof. Okay, now assume G is continuous, then by the construction of product topology, pi x and pi y are continuous maps. Therefore, pi x composite G is a composition of continuous map. Therefore, this is continuous. Similarly, pi y composite G. Is that clear? Should I write the proof? G continuous implies pi x composite G and pi y composite G are continuous. Okay, this is done. So the crucial part is to show the other way around. Okay, assume that pi x composite G and pi y composite G are continuous. Then I want to know, what do I want to know? Whether G is continuous. Yeah, let us go through the proof. Okay, this part we want to prove. To prove G continuity, okay, continuity of G is what we want to prove. To do that, what do I have to do? So what is it? G is a map from where to where? Z to X cross Y. Therefore, let us start with some open set, okay, in X cross Y. So a very natural choice will be I can take a basic open set. Therefore, enough to prove. If I had attended, watch my videos on continuity, you will know this. I would already said enough to show for a very basic open set in X cross Y tau, basic open set, say, okay, G inverse W is in Z, is in tau Z. That's open in Z. Is that clear? But how do the basic open sets X cross Y look like? That's what we did in second lecture. We know that. Okay, sets of the form U cross V, where U is in tau X and V is in tau Y, is form a basis for the product topology, right? Therefore, what we are looking at is we have to look at G inverse of U cross V. whether this is open in tau z. Have you understood? Pause, review, proceed. Okay, now let's as usual look at, if you give me a z in capital Z, when does z belong to G inverse of u cross v? That belongs to u cross v. Remember my mantra, the only way to work with inverse map is z belong to f inverse of b if only if f of z belong to b. That's the only thing. Therefore this means this only g of z belong to u cross v. But g of z, okay, is an element in u cross v. Therefore g of z, how can I write it? I can write it as pi x composite g of z and pi x composite g of, so pi y composite g of z. Do you agree with that? Because the first component I have to get it. It has to be an element of u, right? If I write this as some element x cross y, how do I get this x? This x must be in u. So what should I do? It should be an element of x. That how do I get this? Project g of z onto the first factor. So that's what I'm writing. Do all of you understand? Therefore this is that is same as saying, okay, pi x composite g of z belong to u and pi y composite g of z belong to v. Do you accept it? Because this has to be in u cross v. Yeah, but what is the meaning? Remember that this is a map, its value at z belong to u. This is same as saying z belong to pi x composite g inverse of u and z belong to pi x composite pi y composite g inverse of v. Again, why I am using the way inverse sets are inverse images are defined. Yeah, right. Now what is a hypothesis? Hypothesis said pi x composite g, okay, this is continuous map. Similarly this is a continuous map, right? U is continuous map from where to where? This one is continuous map from z to x, and u is open in x. Therefore this is open in z, and for a similar reason this is open in z. But these are two open sets in z, therefore their intersection is open in z. Do you understand that? Okay, therefore this is if only if z belong to pi x composite g inverse of u intersection pi y composite g inverse of v, right? Therefore what do you think I have proved? I have proved, therefore we have proved g inverse of u cross v is nothing other than pi x composite g inverse of u intersection pi y composite g inverse of v. Go back, because that's why I keep saying inverse images is very okay, students have a difficulty, right? When I said z belong to g inverse of u cross v, what does it mean? I am looking at all those elements in g inverse of u cross v. I am saying z belong to g inverse of u cross v if only if z belong to pi x composite g inverse of u and pi y composite g inverse of v. That means that set g inverse of u cross v is nothing other than this set. Okay, pause, review, proceed. And since this is continuous, we know these are open, and therefore intersection of open set is open. Therefore we have proved g is continuous. Okay, so go through the proof. I cannot repeat. Please learn how to deal with inverse images. Now what is really happening? You see that you, in case of Rn, when you dealt with multivariable calculus even in BSc R2, you would have seen, suppose I have a map from R to R2, I write f is a map, okay, then f of t equal to f1 of t, f2 of t, right? This is equal to xy, but yeah, this x will depend upon t, therefore I call it f1 of t and f2 of t. Therefore I have maps f1 2, and you must have seen f is continuous if and only if f1 f2 are continuous. Okay, this you must have seen earlier in two variable calculus or multivariable calculus, right? So this is what we have done now, because when I have a map G from Z to x cross y, then G of Z must be some element x comma y. This x I am writing as G1 of Z, and this y I am writing of G2 of Z. Now what is G1 of Z? G1 of Z is something other than, I want x out of that. How will I get this? Take G of Z, which is x comma y, and project it on the first factor, that is G1 of Z is nothing other than pi x composite G, and G2 of Z is nothing other than pi y composite G for a similar reason. You understand? Therefore G is continuous if only if this is continuous, same as saying G1 and G2 are continuous. This is reminiscent of what you have learned in several variable calculus. Okay, please understand. Pause, review, proceed. So what does it deal with? The universal mapping property deals with continuity of map from where to where, from a unknown new old space to the new product space. Does it deal with this? No, it does not deal with this. Okay, universal mapping property keeps mum. It is silent on maps of this kind, h from x cross y to z. For example, even in the case of Rn, you know this one, but if I want to talk about continuity R2 to R2, again you have seen that one variable analysis will not do. You want to take it as a whole. Okay, please think about. Okay, don't just think about. Okay, there is no shortcut to prove continuity of a map from R2 to R, but there is a shortcut for continuity of R to R2. I can reduce it to one variable functions. Yeah, f, write f equal to f1 f2, then f is continuous if only if f1 and f2 are continuous. Here I can't do that. Do you understand that? Okay, now come to the last one. Last one is the quotient space construction, where what we had x to y is of f, but x has a topology. Then I put the topology tau on y. What kind of topology? Largest topology. So that f from x tau x to y tau y is continuous. Right? So this is a new object, this is a new construction. So what should I look for? I should look for this one. So I have x, let me write, sorry, so I have x to y, this f is given. Now this is a new construction, therefore I should either look for G from Z or H from Z. Okay, I should look for conditions for continuity of either G is a map from Z to newly formed space Y, or newly formed, say, or H from the space Z to newly formed. Again, I am writing. See, you see that I keep doing the same thing. I don't seem to learn, right, from my earlier mistakes. I'm sorry. Okay, right, either the continuity of G from Z to Y or continuity of H from Y to Z. One of them universal mapping property should deal with. What should be the one it should deal with? Again, what you should look for? I should look for, is there any natural composition for this? So what are the two pictures I have? This one picture and this is the second picture. So which picture admits a natural composition? Here I can't do a natural composition, therefore there exists no natural composition. Here there is. Therefore, what should universal mapping property talk about? It would talk about continuity of a function from y to z. Do you understand? I'm going to change the notation, don't get confused. Okay, so universal mapping property deals with only this one. Let G be a map from y tau to z tau z, then G is continuous if and only if, what is the composite map? G composite F from x to z is continuous. Notice that x and z are already existing topological spaces, but y is a newly constructed space. So what do I want to look at now? So you should never ever confused about universal mapping property, which map you are talking about. Write this down and see where you can find a natural composition, then you know how to formulate it. See, this is the trade secret. In fact, when I explained, a lot of people who knew about universal mapping properties were very surprised. There is a very natural way of looking at them. Okay, so you are into my secret. Yeah, so now the proof is again easy. Okay, suppose F is G is continuous. Okay, G is a map. Okay, then F is already continuous. Why? Go back. F is a map from where to where? X to y, and the topology tau on y is the largest topology which made F continuous. Therefore this is a composite. Okay, F followed by H, that is H composite F. Sorry, now this is G I am talking about. G composite F is if G is composite, since by construction, okay, F from X to y is continuous, therefore G composite F from X to Z is continuous. Are you all right? Okay, so I have to prove the converse. Assume that G composite F from G composite F is from X to Z. We want to prove whether G from Z to Y is continuous. Y to Z, sorry, see, again I am making a mistake. Now you see that, that's why the picture will help me to do that. Yeah, keep the picture in mind, please don't get confused. Okay, maybe I should draw the picture again. Okay, this is my X to Y, this is my map F, and from Y to Z I have the map G. So what I know is this composite, this is continuous. So I want to know whether this map is continuity. So what is question is continuity of this. Okay, right. To check the continuity of this, what should I do? Let the W be in tau of Z, then I have to know whether G inverse of W is in tau of Y. Yeah, but remember, we know what is the largest topology. So now I should say only say tau, because I don't write tau. What is tau? Tau is collection of all, what kind of a map? Collection of all V tau is collection of V contained in Y, such that F inverse of V is in tau of X. Do you remember that? That's how we construct this. The last lecture we did. Yeah, therefore when, are you following? Therefore to show G inverse of W whether it is in tau, what should I ask? This happens if and only if F inverse of G inverse of W is in tau X. Right, this is your V. V is going to be in tau if only if f inverse of V is in tau x. That is, f inverse of this object is be tau x. But what is this? Again, this is a trick with inverse maps. This is nothing other than G composite of inverse of W is in tau x. But do I know that? Notice that G composite of is a map from where to where? G composite of is a map from x to z, and this is continuous, and W is open in z. Therefore, G composite of inverse of W is open. Right? That means I have proved G inverse of W is open. Please go through slow, because many times, I mean, this is where the kind of things which students get confused. Okay, go back. The only way I know a subset is open in the topology tau on Y is by looking at this condition. If I want to say V is open in tau, I have to say whether f inverse of V is in tau x. Okay, right? But what is my V? I want to know G inverse of W. That is my V. I want to know whether it is in tau. That means I have to check whether f inverse of that is in tau. But that, like, okay, the inverse image of composition goes the other way around. Therefore, f inverse of G inverse of W is nothing other than G in composite f inverse of W. But do I know this? Because W is open in Z, and given G composite f is continuous. Therefore, this is open. So I proved it. Yeah. Therefore, G inverse of W is open in Y. Where is it? Open in what is G inverse of W? That is, G is a map from where to where? On Y. This implies G as a map from Y to Z is continuous. So I should keep this picture in mind so that I don't get confused. Okay, please go through, pay attention, learn this. Okay. Now I would like to end the lecture. Okay, now that you have constructed subspace topology, product topology, and quotient topology, subspace and product topology usually is alright. Many students do not have serious problem. With the quotient structure, always they have a problem. So there will be another video of mine which will tell you how to work with quotient sets, then how to work with quotient groups, then how to work with quotient rings, and then how to work with quotient spaces. But I will just, for those who are enterprising, who would like to investigate and explore on their own, who want some challenges, I will say the universal mapping properties play the role of first fundamental theorem of homomorphisms that allow you to identify the quotient groups or quotient rings or quotient modules or quotient vector spaces. This is a trade secret. Okay, you will learn when you look at my lectures on quotient space structures later. Okay, there will be a series of lectures on that. Okay, but this is just a kind of for your own exploration. Okay, so for example, if I have a space X and I have the quotient, I want to identify this. For example, do you remember R2 with this? Okay, we had something like all vertical lines, but all vertical lines are with C, where C is an R. Okay, then I can show this is homeomorphic to R. This space, it's not, I can think of it as vertical line with the quotient topology is nothing other than R with the standard topology. I would like to prove that. In fact, whatever I have done in the last third lecture, it allows me to conclude this. Okay, but I don't want to stop here because there will be separate lecture on quotient spaces. There I will prove all these things rigorously. Okay, okay, let us stop here. So I hope you all enjoyed this, and I know this kind of nuanced, subtle things are never explained. Very easy going things are done, and because teachers underestimate you, that you may not be able to follow it. But I think people who want to watch my videos are curious and they like challenging things. They can do it, and I hope you can do it.